Okay, let's solve quiz 3. So we're thinking of a BCC crystal, and that will come up later in this. We start out by talking about the vacancies in a crystal, and we say there's vacancies. The energy to form a vacancy is 200 millielectron volt. What fraction of the sites will be vacant, assuming 500 Kelvin is the temperature and is in equilibrium? Well, we know that this equation tells us the number of vacancies, negative QV over KT. And we want the fraction, which is NV, the number of vacancies, divided by the total number. So we have NV over N is equal to exp of 200 millielectron volt. And we have the Boltzmann constant, both in terms of joules and in terms of electron volt, so we're just going to work in terms of electron volt. Minus 200 times 10 to the minus 3, because it's milli. That's EV divided by 8.62 times 10 to the minus 5. That's EV per atom K, and 500 K. Actually, this is EV per atom, or I should say missing atoms per site. That. And putting this in the calculator, K's cancel, EV per atoms cancel. So we have unitless, which is important because we have an exponential here, and we get 9.65 times 10 to the minus 3 fraction of the sites that are vacant. Next part of the problem is, given the lattice parameter, determine the concentration of vacancies in units of mole per meter cubed. So we have the fraction that are vacant, so first we need to determine the total number of sites in mole per meter cubed. And we could do this by calculating the theoretical density and so on and so forth, but really this is just a unit problem, right? We're interested in mole per meter cubed. Well, we have that it's a BCC crystal, which means that we know that we have 2 atoms per unit cell, and we have the unit cell length. So what we really have is we have 2 atoms per 3 angstrom, which is, and it's in meters cubed, so we'll do this in meters. 3 times 10 to the minus 10 meters cubed. Now we've got to convert from atoms to moles, and we use Avogadro's number for that. 1 mole per 6.02 times 10 to the 23 atom. And that is going to be 1.23 times 10 to the 5 mole per meter cubed. Well, that's a huge number. But having said that, it is meters cubed, so it's a large amount of space we're filling with atoms. So what fraction of those are vacancies? Well, that is. So we take 1.23 times 10 to the 5 times 9.65 times 10 to the minus 3, and we get 1.19 times 10 to the 3 mole per meter cubed. And we're saying, okay, if you have an edge dislocation, there's an extra half plane of atoms that sits above the dislocation, right? Because we're drawing this as a that. Would I expect the vacancies to be attracted to above or below the dislocation line? So if I draw this in, it's an extra half plane. So in this region, we have too many atoms, too many planes. In this region, we have too few. Right? So this region is in compression. These planes are squeezed together. And this region is in tension. These atoms, these planes are being pulled apart. Compression and tension. And there's too many atoms here, which means that if we could remove some of the atoms, we would reduce the elastic energy, which means that if you have a vacancy, vacancies are going to want to sit where there's too many atoms. So that means the vacancies are going to want to sit here. So when thinking about dislocations and thinking about plastic deformation and strain energy, the way to think about it is either in terms of compression or in tension, if that's kind of a natural way for you to think, or to think about where do you have excess atoms or a deficit of atoms, say above and below, and that tells you about where atoms will move and how dislocations will interact with each other.